Here we head into our next trig identity and equation lesson, double angle formulas. Make sure you have your formula sheet in front of you so you can reference the double angle formulas which I gave to you on that sheet. And we're just going to derive one of them and then just work with the rest of them. Learning goals, again in class, memorize, but virtually just memorize how to use the double angle formulas. What is a double angle? So it's just like our compound angle last lesson. It's an angle that is created by adding two or more angles, but they're the same. So we're not adding like two different angles or subtracting two different angles. We are only adding two or more angles that are the same. And we're going to focus on just two. It gets complicated and messy and fuzzy with more than two. So we're going to try very, very quickly. This is just building off of our compound angle formulas from last lesson. Sine 2x, that obviously is a double angle formula, 2 of x, 2 of the same angle. We could split that up though, 2x, and write it as x plus x. And now it looks like your compound angle formulas for addition for sine. And if you look at that formula, or you have it memorized by now, it is, remember that's like A and that's like B, sine x cos x plus cos x sine x. Now just because the cos x and sine x are in different spots, you're multiplying, so it doesn't matter the order you do your multiplying in. Basically, I have 2 sine x cos x's. So 2 sine x cos x. That is one of your double angle formulas. So we just quickly came up with one of our double angle formulas. I'm not going to bother virtually going into the how you get the other ones, but make sure that you have that one on your formula sheet, plus you should have 3 for cos 2x that we're going to work with. Our first example, express as a single trig ratio and then evaluate. So this is giving you the kind of the expanded form. You got to come up with the singular form, putting it all together into one neat and tidy formula. 2 sine 45 cos 45, that's like our 2 sine x cos x, which I can tidy that up to sine 2x, which in this case would be sine and then 2 times 45. 2 times 45 is 90. So this equals the exact same thing as sine 90, and sine 90 is 1. 2 tan pi over 6 over 1 minus tan squared pi over 6. That is our double angle formula for tan. This is like tan 2 times pi over 6, which is pi over 3. Now for your test and your work, I want to see the special triangle drawn so I know where you got it from. I'm just going to cut to the chase, assuming you're all looking at your special triangles. Tan pi over 3, right? That goes with your pi over 3, pi over 6, 90 triangle, 1, 2, root 3. That equals root 3. You can write root 3 over 1, but it's just root 3. And remember, even though you have to show me the work, how you got it, you can always double check your answer by typing it in your calculator. So in degree mode, you could type in 2 sine 45 cos 45 and get 1, and sine 90 is 1. For B, you could type in all of that stuff in radians with pi over 6 to make sure you get the same thing as root 3. Our second example, if cos x equals negative 2/3 and is between 0 and 2 pi, find the value of cos 2x and sine 2x. Just like the last lesson, this is an example that I like. Makes you come up with a plan, and there's a couple different steps you have to do. So let's start with cos 2x. You have some choices there. Okay, you have a bunch of different choices you could pick for cos 2x. They'll all give you the same answer. Some involve more work, some involve less work. If I'm looking at this question and I'm lazy, which I am, I don't want to do more work. There is one of the cos 2x formulas that involves just cos x, which is helpful because I was given cos x in the actual question, so that means I don't have to do any side work. So what that means is cos 2x equals, if I pick this formula, which you have, 2 cos squared x minus 1, I don't have to do any extra work. I already know what cos x is. So this is going to be 2. Now remember, a common mistake like before, you wouldn't just, cos x is negative 2/3. So don't replace this cos x with cos negative 2/3 because it's going to send you down a dark path you'll never get out of. Cos x is negative 2/3, meaning it equals that. Substitute it. So negative 2/3, and it's squared, right, from the squared, and then minus 1. From there, it's just calculator work. You could type that into your calculator just like you see it. We want to have a fraction, negative 1/9. Perfect. Sine 2x, okay. So we'll do this one now next. So we did cos 2x, perfect. Sine 2x, you only have one option. So that makes it pretty easy. And this is the option. I don't know what sine x is, so I got to figure it out. And because I have to figure out what sine x is, there's actually going to be two solutions. So let's do solution number 1 here. Cos x equals negative 2/3. Drew our Cartesian plane and then put cast in there. Cos is negative in 2 quadrants, which is why there's going to be 2 solutions. Cos is negative right here, right? And here is my little related acute angle. We'll call it A in this case. Cos is adjacent over hypotenuse, or x over r. So 2 over 3. And if we do some Pythagorean theorem, right? 3 squared minus 2 squared equals 5 squared. R equals, sorry, not 5 squared, equals 5. Let me erase that. Getting ahead of myself. So 3 squared minus 2 squared equals 5. That means R equals the root of 5. So this equals 2. Now sine, since it's positive in that quadrant, right? Sine is positive. Opposite over adjacent. So, or y over r, root 5 over 3 times cos x, which is negative 2/3. And doing some very quick math, 2 times negative 2 is negative 4, so we have negative 4 root 5 over 9. There's solution number 1. Solution number 2. And again, we're doing 2 solutions because it tells you x is between 0 and 2 pi. If I restricted the domain to like 0 and pi, or even pi over 2 to pi, there would only be one solution. Or I could do pi to 2 pi, or I could do pi to 3 pi over 2, and the other solution would be just this one down here. Exact same process, just really has to do with adjusting based off of cast. So there's 2, there's 3, 9 minus 4 is 5, that's still going to be root 5. So in this case, though, down here, sine is negative. It's in the tan quadrant. Still opposite over hypotenuse, root 5 over 3, but this time it's going to be negative root 5 over 3. Cos is negative 2/3. Negative times a negative is a positive 4 root 5 over 9. So we have 3 solutions to this, all right there. Any questions? No? Good, great, you guys are awesome. The last thing is more of just like a thought experiment. Could sine x be a double angle formula? We've already kind of encountered this in previous lessons. What about sine x over 2 or sine 4x or really anything? The answer is yes, anything could actually be a double angle formula. Something times 2, for sure you could do that. So let's try. Sine x, if that was a double angle formula, well, what times 2 gives you an x? So 2 times what gives me just a single x? Well, a half an x, right? Because 2 times x over 2 would give you 1. And that would equal 2 sine x over 2 cos x over 2. Let's keep going with that. So what about sine x over 2? Well, sine x over 2 could be sine 2, and what times 2 gives you a half? Well, a quarter. 2 quarters make a half. So that'd be 2 sine x over 4 cos x over 4. What about sine 4x? What times 2 gives you 4x? Well, 2x. 2 times 2 is 4. So this would be sine 2 sine 2x cos 2x, which we could keep going with that. Sine 2x is 2 sine x cos x, and then cos 2x, you could pick any of the 3 formulas for it. And this would just keep going. So this actually has a double angle formula buried inside of another double angle formula. Crazy, I know. There's not much virtually I'm going to apply to this. I just want to point out to you that technically anything could be a double angle. If we were in class, we would do a little bit more with this when we work on trig identities, which we're not going to be doing virtually, and I'll talk about that more in the last lesson of the unit, but comes up again in trig identities as well. That's it. Short and sweet. As always, check D2L for the up-to-date questions that I have assigned, which may or may not be the same as that. And really this lesson was, a lot of these lessons, they kind of set up trig identities, which we're not going to be focusing on virtually. So it just comes down to you referring to your formula sheet and being able to work with those formulas. Thanks for listening, and talk soon.